I apologize for it, but I hope we can understand each other. So P will be the dimension of the process. And let's assume that we want to model this p-dimensional process as a VAR of order D, like written here, and then VAR. Why VAR? Well, VAR is a classical tool in time series, which is useful for forecasting, for impulse response analysis. But, and this is known since long time, but it became more popular recently. VAR modeling also contains information about the interdependencies between the variable of the elements of X, and in particular, many different network definitions can be taken starting from the parameters of the VAR. So, for example, we can speak of Granger networks, which would be related to the coefficient AL of the VAR. We can speak of partial correlation networks related to the inverse of the covariance matrix of the errors. And also by combining the two, we can build this network that you see at the bottom of the page, which is which will be the base of a long-run partial correlation network. This is basically the inverse of the spectral density at zero frequency, so a long-run inverse covariance matrix. And this is something I studied with Christian in a paper of 2019. Okay, sorry, I had a problem with the keyboard. Now I see what I have to do. Now, estimating this model is a problem if we have a high dimensional vector, because clearly maximum likelihood least squares methods cannot work because of the curse of dimensionality. And then the two classical way of challenging the curse of dimensionality in a linear setting are or lasso type regressions, or let's say penalized regression, even ridge type regression, whatever. Sparse models are very popular, which is a supervised learning technique, if you want, with modern language, now that the statistical learning is very popular, or using some sort of factor analysis. Although factor analysis here is still not clear where it kicks in, but I will discuss that later. And when we have lasso sparse models, clearly we are basically dropping the sum of the regressors. When we have factor analysis, it means that the data is driven by underlying common factors, and so we will speak of dense models. Now, being a little bit more technical, there is a nice paper by Basu and Michailidis who shows that if you look at this model from the VAR, so if you look at this VAR and you require stability of the VAR, then you must require uniform boundedness of the largest eigenvalue of the spectral density matrix. That is to say that the second moment, the matrix of second moments should be bounded, okay? Now, this implies also boundedness of the largest eigenvalue of the covariance matrix of X, okay? Now, if we are in high dimension, so we have a lot of elements of the time series, if you want to still ensure stability, then you must assume a very high level of sparsity in the spectral density matrix, or in the covariance matrix, if you want. And this is something that Lin and Michailidis have exploited in their 2020 paper. However, what the data tells us. Now, if we look at economic data, and here when I speak about economic data, I generally refer to macroeconomic data and financial data, which is the data I work on usually. And it's the kind of data where this kind of model has been used a lot. VAR has been used a lot in macro. Then it seems that sparseness is not the rule. It seems that denser structures are more common. And are more of a general feature of this kind of data set. And this was pointed out in a paper, very nice paper by Demore, Giannone, and Reichle in 2008 in Journal Econometrics. And more recently, also in a paper that is becoming quite influential by Giannone, Lenz, and Premiceri in Econometrica of 2021. And in both works, what we see is that some denser structure in the form of common factors seems to be the rule in this kind of data.
May I say something? But don't you think that it really depends what network we're talking about? So, for example, if you talk about true exposure networks, let's say between banks, we might think about either direct or indirect networks, like network of loans or bonds or securities, or like common portfolio exposures. If you look at these true exposures, they look rather sparse. While if you think in terms of the market-based networks, So basically those that can be constructed using the market-based information like equities, returns, volatilities, or like if we talk about the macro data, you're right, like input-output tables, then or like GPs data, coordinated portfolio investment data from IMF, they're quite dense. So it's probably depends on what type of networks you are talking about. So
I totally agree with you. It depends on which kind of network, which kind of data you're looking at. Okay, the kind of data that are analyzed in these two papers that I'm describing do not have a network structure underlying. Okay, there's not a definition of network underlying the data. The network is defined out of the parameters that you see here in the VAR, if you want, but that's the next step. Okay, so this kind of macro data do not the macro data I'm referring are not input-output tables where you really have a network structure. Is classical macroeconomic data set like used by Stock and Watson in all factor analysis, where you have many macro variables and you just want to see what are the dependencies between these. And so then you see that there is some co-movement among the time series. Okay, so I totally agree that there might be cases in which what we're doing here is not relevant. Okay, so I just buy your point. Let me just say that the kind of data that is analyzed in this paper is so what we will analyze, and I worked on in the paper with Brownlees. I also did a research on that, which was a panel of log volatilities of stocks of the S&P 100 or 500, I don't remember. And basically, again, there you do not have a network structure if you just take the time series like that, but you use a network representation to highlight some certain dependencies. And if you want to find them, you probably need to control for common factors first, which will otherwise make all the imputed network as a dense object. I will show you a graph in a moment, starting from a paper that did something like that, hoping to convince you that in that case denseness is something of a problem. So going back to this kind of data that I have in mind again, so there is also some literature in financial markets where you always have, where you often have a systematic component, if you want, the market, which is something is not diversifiable, that is common to all the elements that you have in your panel of data. And then, so basically, if you take a panel of stock returns and you compute the first common factors, that's basically the stock market index, nothing else. It's just a weighted average, okay? But it captures a lot of the movement of these. But on the other hand, of course, there are sectoral or individual specific movements that you do not capture after that you might want to investigate. But a good idea is first you control for the market and then you investigate the other part. That's the idea from that point of view, okay? So there might be global factors, but there might be idiosyncratic factors, which can be idiosyncratic with single series. So just, you know, a company that is hit by a specific shock and then carries with it all the others afterward, which is the idea of a systemic risk, of a systemic company that is problematic, as we had it during the financial crisis. And in that case, those shocks are less diversifiable. I mean, are diversifiable because, of course, you can invest on something that is not affected by these shocks. Okay, so this is something on which Christian has worked much more than myself. So this stands as a motivation, but if we buy the idea that there is some common factors underlying from a technical point of view, again, we go back to the point of what happens to the eigenvalues of the spectral density matrix or the eigenvalues of the covariance matrix, even in a simpler case. Well, if there are common factors, then these eigenvalues tend to be, are spiking, must somehow, I don't want to be too technical now, spiking as the number of series grows, okay? So the more series you add, the more the part driven by the common factors becomes relevant. But this is at odds with the requirement of a stable VAR. So if you want a stable VAR, but you have common factors, you first have to control for the factors and then estimate a sparse VAR. That's the bottom line of this introduction, okay? So you first address the dominant autocorrelation by means of common factors, and then you impose sparsity on what is left. And that is what we do here. Now, going back to your question, and this is taken from a paper by Biglio and co-authors, which was published in 2012. And this is a network diagram of linear Granger causality relationships, statistically significant, for this kind of data. Now, let me just give a disclaimer. I'm not an expert of finance, so I just took this description, okay? So you're probably more expert than me, but this is what they look at. They take this kind of data. So 25 largest banks, broker dealers, insurers, and hedge funds over this period. And this is an influential paper. That's why I wanted to point out. So basically, they take all these elements and they test for Granger causality pairwise. And if each time you have a statistically significant Granger causality relationship, they draw an edge between the two elements. And now what you get is a network. I mean, it's not that everybody's connected with everybody, but still this is quite dense, okay? Which is fine. I mean, this is what the data says. I'm not saying it is wrong, but I'm discussing what is the usefulness of this kind of network representation. Maybe there is something common that you want to control first, and then try to draw this kind of graphical representation and derive some conclusion from it. Because of all these things, what we consider here is a generalized dynamic factor model plus sparse vector autoregression model. So we have this X panel of time series, which is divided in two components, the chi and xi component. The chi component is the so-called common component, can be written as an infinite moving average. BL is a filter times UT. UT, it's let's take it as the simplest case, IID 0, 1 vector process of dimension Q, where Q is much smaller than P. So Q is the number of factors here, okay? So this is a low rank component. And then there is an idiosyncratic component xi, which we are going to model as a VAR, as in the third equation of this slide. And we will impose some sparsities on the coefficient of this VAR model. And then we study the estimation of this model. So the common component can be estimated with dynamic principal component, but this is known. So this is not our contribution. Our contribution goes in the second and third bullet point, where we study estimation of the idiosyncratic partial correlation network, the way defined before, through L1 regularization. But this is a second step. So first you have to control for common factors, because xi is unobserved. So you cannot directly estimate a sparse VAR on that. Now, it seems obvious. One might think, okay, you get an estimator of xi and then you go to the coefficients, but that's not exactly what we do. We do not estimate xi. We just estimate second moment of xi. And this is what makes the technique quite useful and quite interesting, I think. And what we show is consistency rates of all the estimated quantities as both n and p go to infinity. There is a lot of stuff. I probably don't have time to cover all of this. I will try to give you the main ideas. Okay. This comes from another work of mine that I did with Mark Allen, where I exactly use the structure that I just described. And this is the zero frequency spectral density of a panel of 90 log volatilities. The one on the left is for the observed data. The one in the middle is for the common component. You see it's very dense because there is a common factor driving all the dependencies. And the one on the right is the residual idiosyncratic component, where you have a more sparse structure, but you also see clusters, okay? And clusters corresponds to sectors. Exactly, the one in the red square are financial top left and electricity bottom right. So you see there is a lot of structure that you already see this group structure in the axis, but once you clean for common factors, you see it much better. Okay. So now what I always talk about dependencies, I'm speaking about linear dependencies. I will just work with linear models, linear dependencies. So I don't look at no linear dependency, which is of course interesting, but we didn't do it in this work. And the other question is, do we care about conditional or unconditional dependence? That is to say, we look at second moments or something related to inverse second moments, because this is also distinction. What is sparse, what is not sparse? And typically networks definition, as if you go back to the literature on graphical models, is about conditional dependencies. And then dependencies can be at the same point in time or can be lagged or leads. And if we work with time series, which is all about autocorrelation and autocovariances, it makes sense to study dynamic dependencies. Okay, so this is to give a general idea of what are the challenges ahead. Now there is literature this paper speaks with different strands of literature. Literature on sparse VAR and large sparse VAR. There are a lot of papers, quite recent, most of them. Song and Bickel, Basil Michaelidis, Koch-Callot, Davis and co-authors, Medeiros and Mendes, and my paper with Christian can fit on that also. It was about networks, but in fact, we were estimating a large sparse VAR. There are other works, more recent, probably less well known, mainly by Michaelidis, where they still study this sparse VAR. They make other assumptions. They make a low rank plus sparse assumption on the coefficient of the VAR, which is interesting, but is a little bit odd because the low rank component does not really reflect pervasive factors. So it's just a way to try to reduce dimensionality in a different way with respect to what we do. Okay, then there is literature on networks in time series. As I said, this is something that goes back. I mean, in econometrics, the oldest paper that I could find was by Dalaus in 2000. It might be even older papers. Then the paper by Billy and co-authors, from which I took the picture that I showed. And then there is a very influential paper by Diebold and Ilmath, who also exploit the VAR representation, large VAR representation. Actually, that's not very large high dimension. They do it for 20 stocks, so it's moderately small dimension. So they don't need any sparsity or this kind of tools. Then there is a lot of literature on dynamic factor models, but what is relevant for us here, that dynamic factor models can be written or with the dynamic loadings the way I showed you, so BL times UT, an infinite moving average. So there are few factors loaded with infinite, possibly infinite legs. And this is all the literature by Forney, Hallan, Lippi, and Reiklin, with all the developments starting from a paper in 2017 with Forney, Hallan, Lippi, and Zaffaroni, and then going back also to some works that I did with Mark related to volatilities on that. And then a simpler setting where the loadings can be just static is also interesting for us. And here there are some other references. And then the question is, are we the first to bridge factor and sparse models? Well, actually, this is something I did with Mark Allen in an empirical paper on GRSSC a few years ago, where we did, that's where I took the pictures that I showed you, but there was no theory there. There is some theory, very recent, as you see, essentially by Jianxin Fan and co-authors, but everything they do is with static factor loadings, and there is no dynamics, basically, okay? So it's true that it applies to time series, but they really do not account for leading and lagging dependencies between the variables. So if you want, theirs is a special case of what we're doing here. I'm not saying that it is not a nice paper, especially the 2022 paper is a very nice paper, very nice reading if you're interested in this stuff. Now, a little bit, but I promise not too much technical. We go back to the model that we had. So our data is decomposed into a common and idiosyncratic component. The common component chi t, as we said, is an infinite moving average driven by few shocks, UT. So UT is of dimension Q, and Q is smaller than P. Actually, Q will be finite, but all asymptotic will be for P that goes to infinity. So even if P goes to infinity, Q stays finite. Okay, so that's what defines the reduced rank structure. And then, as I said before, we can write a VAR of order D, where D is finite for the idiosyncratic component. Now, this is the representation I started from, but there are other useful ways of writing this model that highlight different aspects of different things that we can do with this kind of model once we estimate it. So that's what I'm going to do now in the next 3 or 4 slides. Okay. Well, the first thing that if we have a VAR for the idiosyncratic component and D is finite and the VAR is stable, then of course we can invert it and get the infinite moving average representation of also for the idiosyncratic component, which will be useful for stating the assumption. Okay, so the idiosyncratic component can always be written as an infinite moving average, D of L times so gamma to the 1/2 is just to give a covariance to the epsilon. Okay, this was for convenience. We wrote the model like that. Okay, I could have had innovations already with covariance gamma. It wouldn't have changed anything. Okay, so this is trivial. There are other useful representation though that is useful to discuss. Again, I want to point out the fact that once we have psi, we can define a series of networks for psi, so networks for the idiosyncratic component. On the other hand, and this is probably less well known, if we look at the model for the common components, so the second equation in this slide, this is an infinite moving average, but this is a singular moving average. So the question is this invertible? I mean, can I get an autoregressive model for chi t? This is not so obvious if you think about it, okay? Well, actually, there are interesting results that show us that there is a vector autoregression representation for the common component, which has some particular features that I'm going to say in a moment. But why do I care about that? Because if I have a VAR for chi and a VAR for psi, then I can estimate them, and then I can forecast chi and psi. So if you care about forecasting, this is a useful representation. And then I want to show you that this is basically allowing us also to study large factor augmented vector regression model for the data, going back to works by Stock and Watson and Bayanang. This is just to create a connection with other literature on factor models.
Sorry, Matteo, may I have a question,
sure.
please?
Yeah, go ahead, please.
Do I get it right that so you think about such approaches, like, for example, you mentioned Diebold-Yilmaz, right? So originally think of a bunch of banks, of bunch of companies, yeah, and you get either volatility or returns for them. And then you can put them directly, like Diebold-Yilmaz or Dimaya et al. Into the big VR, estimated with an adaptive elastic net, for example, or LAS or RIGI, and then construct a network. But what you're saying is that the network that you obtain is not only it has two components, basically. The connections that you see might be due to either common factors or idiosyncratic, like the connections. And what you want to do, you would like to separate the two.
Yes.
And like the method that I know, for example, it's like you can do, as you suggested, principal component analysis, and then you regress on factor, you get the factors, you regress on factors, you get the residual, and then you insert the residuals into the same VR, you do your estimation, and then separately you will get already the network, which captures just the idiosyncratic component, because you remove all the common factors. But what you offer here, do I get it right? Like, this is my question. Do I get it right? That the novelty and the contribution of this approach is that you do simultaneously estimation of two types of networks, and you can forecast later on the first one, the idiosyncratic, and as I see, the common. But
well, no, actually, I don't do it simultaneously, but I do it in a slightly different way with respect to the way you said it. I never recover an estimate of psi. I can go directly to estimate the coefficient bypassing psi, because estimating psi, which is a large vector of random variables, gives a lot of problems. I mean, you can get very large errors there, okay? What I managed to do, let me go one slide before. So, okay, look at this one. What I managed to do is to estimate the coefficient A starting directly from the second moment of psi without estimating psi. So basically the idea is without the spectral density. Okay, think it in time domain. Well, no, I have to think. Okay, so I can get all the autocovariances for chi and psi, starting from the spectral density of X. And once I have the autocovariances, I can estimate A using autocovariances without using psi, like Yule-Walker estimation. So this bypasses psi, you see? I mean, but this is a two-stage. It's a two-stage. It's not a one-stage estimation. I mean, I don't know of a way of doing it in a one-stage. I don't even know. I mean, I have no idea how to do it in one stage. I mean, there are works that do it actually, but I don't want to enter too much. Okay, I mean, now I think of a way of doing it in one stage. Okay, but we don't do it. So let me be.
Yeah, I got it. Thank you.
Okay.
And maybe one more question, and then I will shut up. One more question. Like, what does it mean if you go to the next slide?
Yes, this one.
No, next.
Sorry, this one. Yes.
Yes, VR for common.
Yeah, I'm going to show you. I'm going to show you in a couple of slides.
Thanks.
So 1, 2, 3 is what comes next. Is not finished here. There is one slide for each of the three. So if you give me 1 minute, I'll get there. Okay. Okay. Let me get there. Okay. So first, idiosyncratic networks. This is something that was already in the first slide, but let me be a bit more formal. Okay. So we have a VAR for the idiosyncratic component, which is written at the top of the page, and I can define, and I will give consistency results for the following three networks. The Granger networks, which is a directed networks with a set of edges EG, which is basically defined there is an edge between node I and I prime whenever at least one of the coefficients of the VAR, the entry I prime of one of the coefficients of the VAR is not 0, okay? This is not ideal because when you sum them, there could be cancellations. So this could be made a little bit more robust, but whichever kind of result we derive can be applied to different definitions of Granger network. Okay, so we will have a result of consistency for A. So once you have that, then you can do whatever you want. Then there is a contemporaneous network, which is once you call delta the inverse covariance matrix of the innovations of the VAR, then the contemporaneous network has a set of edges EC, which says that there is an edge between I and I prime, where I and I prime are different, two out of diagonal entries, which is defined with the formula that you have here. So minus delta I prime divided the square root of delta I prime. This is exactly what defines a partial correlation. Okay. Okay, and then as I said, you can build a long-run partial correlation, which is basically the inverse of the zero frequency spectral density. So long-run covariance matrix inverse. The 2 pi is there, but it's really irrelevant in the definitions, but it should be there. But basically, it's the long-run filter A transposed 1 delta, so the inverse covariance of the residuals, and then AXI 1, so the long run. And then once you have this matrix omega, you can build a partial correlation with the same definition that we had before. So these are the three networks that we're going to discuss, and they capture different aspects. Okay, the first one captures the dynamic dependencies. The second one captures the contemporaneous dependencies given the dynamic dependencies. And the third one puts everything together. And what is interesting is that, of course, there are non-zero edges in omega whenever there is a non-zero edge in delta or in A, but there can be non-zero edges in omega that are the result of the combination of the two. So the structure of omega is richer than the structure of the two separate. Okay, this is something we showed in the paper with Christine. So going back to your question, what is a VAR for the common component? What do I mean? So we have this model for the common component, the first equation. The common component admits this infinite moving average representation, singular one, okay? This is a very general result in the works, proved in works by Lippi, Hallen, and Forney a long time ago. There is an econometric theory by Forney and Lippi of 2001, which shows that this is a very general representation for a stationary time series. But aside these technicalities, what turns out that if you have a milder assumption that the spectral density of chi is rational, basically it means that B of L can be written as a ratio of two finite degree polynomials. But forget about that. It's very general. You can always write the same equation, the first equation, as in the way you have in the second equation. So that is an autoregressive model for chi, where A chi is an autoregressive filter of finite leg S. So be careful. I'm saying that I can invert an infinite moving average in a finite VAR. That's not the rule, but this is the rule due to singularity. This is an important result by Anderson and Deisler. Okay, there exists a finite S such that I can write this thing, and the other thing is that A of L will have some block diagonal structure. Now this is very technical, and it might take 20 minutes to explain only that. So since this goes in other papers, I'm happy to discuss it, but I prefer to leave it at the end of the seminar. If someone is interested, then we have time. Okay. I'm not that I want to hide something in the paper. There are all the details, but it really takes a lot of time. The important thing is that I can write a certain kind of VAR for chi. And if you look now, the filtered process AL of chi, this left-hand side, is a p-dimensional process, which now has a static factor model representation, because R is the matrix of static loadings and U are the factors, okay? So, I mean, if you know A and you can filter this, then you can do PCA to get R and U, basically. And the fact that U are common factors is captured by the fact that R prime R is an exploding matrix with the dimension of the process, meaning that the factors this U are pervasive for all the cross section. Now, in this case, it's true that I can write a VAR for chi. Okay, so you might wonder if I have a network interpretation also in this case, but the answer is no, because I have fewer shocks than nodes. I have P nodes, but I have Q shocks. Why that? Because these shocks, if you want, you should interpret them as global shocks, shocks that do not originate from a specific node. Okay, so while I look at the VAR for the idiosyncratic component, I can think that each node generates a shock, and then I look at how it propagates to the system. That's the view by Diebold and Ilmaz, essentially. I cannot replicate the same view by Diebold and Ilmaz here, because this singularity means that the U are common to everyone, so they're not specific to a shock. So I cannot write any kind of network structure here, okay? But still, this is useful for forecasting, because if you manage to estimate the A chi and the AXI, and this is only the lagged part, okay, of the two polynomial, then X can be written in this way here. And then, of course, I can do prediction of X one step ahead. For example, is the one step ahead prediction of chi, which is this term here. And the one step ahead prediction of psi, which is the other term. And then, of course, UT and epsilon T are innovations, and they are just the one step ahead forecast term. So if I manage to estimate all these coefficients, then I can do predictions. Prediction is another thing, it's not network. Okay, so with this paper, we can do two things. We can do network analysis, which is the main bulk of the paper, but on a side, we also discuss the fact that we can do prediction. I don't think I will have time to enter details of predictions, but that's something I wanted to point out. Last thing is that, in fact, if we restrict the fact that the factor representation as an infinite moving average to a finite moving average, then we can always write the model in the way that you have at the bottom of the slide. So that XT is actually a linear combination of factors capital FT, which are contemporaneous, plus an idiosyncratic. This is the standard factor model that I'm sure you've all seen, okay? But the factors in turn are autocorrelated with a certain kind of VAR structure, whatever that is. If we buy this assumption, I mean, if we go for this kind of factor modeling, then a series of substitutions show that we can end up writing a one-step ahead prediction for X, which is a function which depends on common factors lagged, this first term, so C of L ft minus L plus 1 with some lags, and then the lags of all the other variables. So here you see that the VAR structure is there, the second term on the right-hand side of the last equation, but we also have the factors in front. So this somehow should close the circle from where I started from, okay? I started from a VAR with X, I said I want to control for factors, and then I show that if you control for factors, you can still get a VAR for the X's, but it's a VAR with some additional regressors, which are the latent factors, okay? I think this is quite interesting to see. So once we have a result for our estimation, then you can pick the representation that you want of the last three that I showed you and do prediction, do regression, do whatever you want, okay? But by using the approach that I'm going to describe, you can basically have both the factor part and the idiosyncratic sparse part together modeled, okay? Modeled together, but estimated in 2 steps. Okay, so there are a certain series of assumptions. Now, it's quite late. Let me just say that the filters have some summability conditions that ensure that autocovariances are decaying at the speed which is fast enough. This is geometric decay. I mean, this is slower than the usual geometric decay. Okay, but it's a technicality. Think of geometric decay, it's fine. And then let me give you only the main assumption, which is if we write the spectral density matrix of our data, which is basically the sum of all the autocovariances gamma x of L times some weights, this is the usual Fourier transform, then what we need to assume is that the eigenvalues of the common component, mu, chi, j of omega, which are just q because that's singular, diverge linearly in P. This is, and they are distinct. This is what the first assumption says. And the idiosyncratic eigenvalues of the spectral density are bounded. Remember that this second assumption is exactly what guarantees the stability of the idiosyncratic VAR. And the divergence of the dynamic eigenvalues of the common component says, meaning in linear in P, means that every time you add a new time series to your panel, this helps in recovering the factors and helps in separating the common part from the idiosyncratic part. So in this sense, since these assumptions are stated for P going to infinity, we have an asymptotic identification of the common idiosyncratic component only asymptotically, only as P goes to infinity. And this is typical of large factor models. So there's nothing really new there, but if you have never seen that, that's what you should get from the idea of large dimensional factor models. And this is from data from Basuli and Michailidis, the data that they analyzed, which is again a panel of 46 volatility measures. The first two eigenvalues of the spectral density computed using subset of the data, either just two time series, 4, 6, 8, up to 46. And you see that the more you add series, the more the first eigenvalue diverges away from the second. So the more you can separate the two components. This I think it's a very nice graph because it gives you really the idea of how increasing the dimension helps in disentangling the two. And in this sense, having a large dimension is not a curse of dimensionality, but it's a blessing of dimensionality, because you see, the larger is P, the more the two components are separated. And then this is important. What do we assume for the innovation of our process? We have U, which are the innovation of the common component, and epsilon, which are the innovation of the idiosyncratic component. We can work under two settings, but the interesting one is the first one. The first one says we just assume that they have at least 4 moments. That's it, nothing else. Then, of course, we have results for the Gaussian case, but these are just for the sake of comparison with other existing works. Okay, actually, the Gaussian case is nested into the first one. So I will show you results for the first one. Okay. We're actually working now on robust estimation where we just need 2 moments, not 4 moments to exist, but that's ongoing research.
So 4 moments is not sufficient.
Nu greater than 4. So at least 4 moments, that's enough for our result to hold. Okay, but then we will have rates that depend on nu. So I will show you that obviously the rates depend on nu, and the smaller is nu, the worse are the rates because the tails are heavier. Okay, so I think it's nice because we can really track this nu in our rates.
Thank you.
Okay. So estimation goes, you just estimate the spectral density with the usual periodogram with the bandwidth. So smoothing the autocovariances, bandwidth M. There are standard rules to choose M. Basically, think of order of n, the sample size to the power of 1/3, which is what we choose, which is the optimal trade-off between bias and variance. And then you do principal component analysis at each frequency omega k. So you can write eigenvectors E, eigenvalues M for the spectral density of the data. And then if you retain just the Q largest eigenvalues, basically you have an estimate of the spectral density of the common component. And the spectral density of the idiosyncratic component is just obtained by difference, taking the one of the data minus the one of the common component. And basically this is the first step. So you get the spectral density of the common idiosyncratic component by dynamic principal component. Dynamic in the sense that you do principal component analysis at each frequency, okay? But for the rest is standard principal component analysis. This is a method put forward by Brillinger in his book on time series. Okay, and then we want to estimate the VAR for the idiosyncratic component. So let's say that we have a VAR1 to make notation easy, otherwise it's really cumbersome, the notation. So once you have a spectral density, sigma hat of psi, you just do inverse Fourier transform, and you get the autocovariances at all legs, L, for a finite number of legs. But we have a VAR of order 1, so we just need gamma 0 and gamma 1 here, okay? So the covariance and the autocovariance of leg 1 of psi. And then basically we estimate the coefficient of the VAR by this minimization, the first one, the constrained L1 minimization. This is a Yule-Walker equation, the one in parentheses. we minimize the trace of this distance subject to an L1 penalty, okay? And as you see, we do not need an estimate of psi to solve the problem. We just need an estimate of the autocovariances, which is much easier to control. I mean, the error of this is much easier to control. So this is one, from the theoretical point of view, this is our most important, from not theoretical, let's say methodological point of view, this is the most important contribution because we are the first one of estimating in this way the VAR for the idiosyncratic component. While the Jensen Fan paper, it just gets an estimate of psi and then does a lasso regression. Okay, so his rates might be more difficult to control. Of course, one can think of other minimization. We studied Danzig selector, but I don't want to speak about it today. Okay. So now hereafter, every time I write a matrix with these two bars and infinity, I mean I'm taking the maximum of all the entries of the matrix, okay? And when I write with the 1, is the sum of all the absolute values. Now, once you have the VAR coefficient, you can estimate the covariance of the residuals. You can obtain a regularized inverse of the covariance of the residuals by solving another minimization like the one written here. This is not new. This is in a paper by Candes and Tao, I think. So we just borrow from them. And then you can basically build an estimate of the long-run partial correlation matrix by plugging in all the estimates of the previous two steps. Now, I just want to show you a few things about the rates and then go to some numerical results. As I said, we consider two cases, the Gaussian case and a general case where we just allow for at least for moment to exist. So I will focus only on the first case. So I will use this var theta, okay? This will be one piece of our rate. What does it contain? Look first at the second part. If there is not the p, basically what you have under the square root is the classical variance of the periodogram, the square root of m, which is the bandwidth divided the sample size, okay? The log m is because we want results that are uniform across all frequencies, but up to logarithmic terms, this is a classical term that you get. The p you will see later why it's needed, okay? But just to give an idea, to fix the ideas, this is the classical thing that comes from estimation of the spectral density. This other term is a little bit more complicated and less intuitive. It depends on nu. So you see, the more moment you have, the more nu is large, the more the terms in nu disappear. Well, okay, 1 over nu, if nu goes to infinity, those goes to the exponent goes to 0. But you see, as long as nu is finite, there is a p here that appears, which accounts for the fact that these are heavy tails, and so when you have a large dimensional data set, this will affect your estimation. Okay, so this I mean that theta var theta, the terms here is the maximum of one of the two. Okay, this notation means take the max between these two. The one below is the Gaussian case. So if nu goes to infinity, the first term basically is always dominated by the second term. And so you just keep the second term. But I will not consider the Gaussian case anymore. Now, the nice result that we have is that if you properly pick the bandwidth for estimating the spectral density, you have this result. So this is a uniform result. This is the max over all the entries of ij entries of this matrix. And this is a large dimensional matrix. Okay, this is the max, the soup over all the frequencies, and the max over all the entries ij of the spectral density of the common component minus the true spectral density. This goes to 0 with 3 terms. So we have 3 terms in the rate. And then the same rate goes for the autocovariances, goes for the spectral density of the idiosyncratic component and the autocovariances of the idiosyncratic component. You see, the rate is always the same. So let's see what the rate is and why we derive that. And then I will skip mainly the rest of the theory, because then this rate is the same rate that carries on to all the other steps. Okay. So there are 3 terms. This second term is the bias that you get in estimating the spectral density, classical term. Then there is var theta, and there is 1 over square root p. Now, the 1 over square root p comes from the fact that I need to separate common and idiosyncratic components. So you see, again, if p goes to infinity, that goes to 0. That's asymptotic identification of the common idiosyncratic component, as I said before. It leverages. What does it mean, OP? OP. OP is probability. So the probability that this object here is greater than a constant goes to 0 with this rate. Okay. It's convergence in probability, this one.
Oh, thank you. Mm-hmm.
Okay, you're welcome. Yes, I should have written it more properly, but there is not much space for all the notation. But this is what I mean. With OP is convergence in probability. And this is the rate, the one in parentheses. So the max between these 3 terms. Okay, so everything is based on a concentration inequality by Zhang and Wu. which says that if you take the probability of the sup over all frequencies and the max over all the entries of the spectral density matrix estimated for x minus its expected value, being greater than a certain z, where z is any positive number, this is less or equal than the sum of two terms. The second term is the classical Gaussian term, you see, with the p squared, because there is this max over I prime inside the probability, okay? But this is a classical Gaussian term. The m comes from the sup of the frequencies because I have m frequencies. The p squared comes from the max of I prime. And then this is the classical Gaussian tail behavior. And this is a power law behavior, which depends on how many moments you have. Okay? So this paper by Zhang and Wu, which was recently published in the Annals of Statistics, is crucial for our approach. And it holds for processes which have a bounded physical dependence, which is a different definition of a dependence in time series introduced by Wu in 2005. So there is no mixing assumption here. We work with this other definition of dependence, which is an alternative, I think. And I mean, there's not an exact match between mixing on this other kind of dependencies and this one. So everyone picks the one that prefers. I mean, so we use this kind of approach. Okay, and then I said we have three terms. So this theta, remember, is the one I showed you before. This accounts for possible heavy tails in the sense that if I have only 4 moments, this would be very, very important, this term here. The bias term I discussed, and then there is a term that depends on P, which is the one that needs to separate common and idiosyncratic component. Now, just to see what is the relation between NP and the number of moments, I just want to point out that if P and M grow at the same rate, then it's enough to have really 4 moments to exist. If, however, P grows as n to the alpha, where alpha is greater than 1, so for example, n squared, so we go to much higher dimension, then we need more moments to exist for making this thing to work. And if actually we go to the ultra-dimensional setting where the number of series grows as the exponential of the sample size, which is really the ultra-dimensional setting, then we cannot get any rate unless we assume sub-Gaussian tails. This is quite standard in the literature. I've seen that Jianxin Fan in his paper has more or less the same kind of result, although from a different approach, but the bottom line is the same, okay?
Matteo, may I ask if the
yes.
considering heavy tails, a finite force moment assumption, can that be relaxed?
Okay, yes, thank you. Yes, I know that saying heavy tails and then assuming finite force moments is a little bit odd. We're working on that. Dana Zhang, who is a student of Wu, has similar inequalities for the case where you have only 2 moments. So yes.
Mm-hmm.
But then you need some robust estimator of the idiosyncratic of the spectral density matrix. Okay, we cannot use this estimator. You need some robust estimator. Standard stuff, but never applied in this setting. This is something we are working on now. So thank you. That's an excellent question, and indeed it's something we are really working because in high dimensions, just for the fact that you have so many observations, tails become heavy. So
that may be important for financial applications.
Yes.
For instance, for financial returns, typically force moment is infinite, tail index smaller than 4.
Yeah, I agree. For returns, that would be very important. Our application is on log volatilities, so they tend to be, I mean, someone says that they are almost Gaussian, so okay. But I agree that if we go for returns, that would be important, and we definitely are exploring that road. And I mean, we have theory already. We want to see how it works in practice, but the theory that we are developing is for only second moments to exist.
Thank you.
Okay.
And here, okay.
Sorry?
No, here new is just a moment which have to exist, huh?
Yes.
Okay, thank you.
If P is not too much larger than N, then nu greater than 4 is enough. But the larger P gets, the more moments you need to still get some consistency result. Basically, that's the idea. Okay. Keep in mind that I'm showing you results on the max. These are uniform results. We have in the paper results for the Frobenius norm. So those results are less affected by the heavy tails. Okay. But these ones are the uniform ones. Okay. So this is the worst case scenario. Okay, so then, as I said, this kind of rates with certain set of assumption on the constants of the lasso part and the other penalization carry on to all other steps. And I don't have time to do all of them, but let's say that if we properly threshold the estimator of the lasso estimator of the coefficients of the VAR, then we have a consistency for the long run partial correlation networks omega hat minus the true one. Again, this is the uniform, this is max over all the entries of this error. And this is less or equal than two terms. S out and S in are the in degree and the out degree associated to the Granger network, okay? And so there is an interplay between the two. The first term comes from estimation of the VAR. The second term comes from the second step. Once you estimate the VAR, you get the residuals, you estimate the covariance of the residual, you estimate the inverse of the covariance of the residuals, and that gives you the second term. And obviously, both of them, the in degree and the out degree, enter because in the definition of omega hat, you have both A and A transposed. So they both enter for this reason. Okay. This is something that by itself to enter all the details would take long. So I just want to give you ideas. Okay. Then prediction I will skip because there is no time. If you're interested, we can discuss later. I want just to show you some simulations. So we have different simulation designs for the idiosyncratic component, either Gaussian and homoscedastic. This is spherical. This is the non-spherical setting. Still Gaussian, and then student T with 5 degrees of freedom. This is normalization constant. Okay, and then for the common component, we consider three cases. The case in which there is no common component, which is called the oracle. So we observe psi. The case in which the common component have an infinite moving average, so two factors, and the case in which we can write the common component with those factors that are loaded contemporaneously that I showed you at a certain point. So lambda times capital F, okay? And those are 4 of them, and 2 shocks driving 4 of them. So that's probably something that I didn't say much, but there are 2 ways, 2 kind of assumptions that I can make on the common component. The C1 is the so-called unrestricted case, and the C2 is the restricted case. The C2 is the one that you see in Bayeneng, Stock and Watson, and that kind of literature. The C1 has been studied basically only by Fournier, Allen, Lippi, Reichling, Fournier, Allen, Lippi, and Taffaroni. Different combinations of N and P, and what I want to show you are the ROC curves. So true positive rates against false positive rates. What we have here are curves for different configurations of the penalty, and you want to have 0 on the horizontal axis and 1 on the vertical axis to minimize to maximize the true positive rate and minimize the false positive rate. Okay, the dashed line is the 5% false positive rate as a benchmark. Now we have different lines. So you have solid line for Danzig selector and dashed line, dotted line for lasso. So I just spoke about lasso, but as I said, we did also everything with Danzig selector. And then basically here you don't see anything. You see that when N and P go to infinity, we get very good results. Okay, the bottom right panel shows us that in all the settings considered here, everything works well. This is estimation of the VAR, same other settings here, same thing. Now omega is a result of 3 steps. So here things can be more complicated. And so you need larger N and P to get somewhere. But eventually we also get good results. And then this is a little bit less nicer. Here we are considering E1 and E2. Sorry, this I think it's wrong, the caption, because E1 is the homoscedastic case and E2 is the autoregressive case, and I don't think that the autoregressive can be so much better than the homoscedastic. That might be the other way around. I think these are E2 and E3, and so the E3 is the heavy tail. So here we still have to see what happens, because the E3 seems to me not well. I'm sorry, here there is something wrong. I realize it only now. So I mean, there is one case in which it doesn't work so well, but I thought that this, let me see, no, okay. I thought that this was the case when we have the unrestricted common component. It has to do with the common component, not with the idiosyncratic component, but is not from the caption. So, well, I don't remember. I'll check the paper later, maybe, if we want to discuss that. This is estimation, but I want to show you a result, empirical result. Okay, so panel of volatility, 46 stock prices. These are the one in Lin and Michailidis paper, just for comparison with their paper. Okay, so 46 is not so big. We use volatility measured as a high-low range, definition by Parkinson long ago, and then we take log volatilities. Okay, so our axis is the log of the sigma square. And then we estimate on rolling windows. Rolling windows of 1 year, 252 trading days. These are the network, the Granger, the contemporaneous, so the one on the errors and the long run. This is in 2006, 2007. And then if you go on, so only the colored dots are the non-zero edges, okay? The other dot, the light, not exactly white, but almost white is 0. Then it becomes more dense when you enter the financial crisis. This is known. And then something for some groups of stocks becomes more important, their role in the connections. And then when you go to 2010, everything is full, but here the sign is reversed. Okay, so blue is negative and red is positive. Okay, I still have to make a little bit of more sense on that. Admittedly, this is not a paper of finance. This is a statistical paper. And I'm not a finance person, so I can see something, but it's difficult for me to build a proper story out of it, honestly. What I want to show you is forecasting. Because
sorry,
yes.
Matteo.
Yes.
Like I don't know if that might be helpful, but at least I think with partial correlation networks, like when there is negative sign, what we were thinking, it can be a diversification. So like if it's a positive sign, imagine that there will be a shock to one bank and then return drops, or like volatility rises, and then it will rise also on another bank, right? So that will be a positive correlation. And that's what you observe on the left. But on the right, like if one is worse off, the other is better off. So it can be maybe thought in terms of diversification.
I think that this is what you see going from 2008 and 9 in the high part of the financial crisis. You have most positive, and then afterwards it becomes negative. So it might be a reaction to that. Just looking at the right-hand side, okay? I'm just looking at the one on the right-hand side in the 3 cases. You see, it really changes the picture. Becomes more dense, but positive. Becomes very dense and positive for one particular stock, and essentially for the ones in this red group, which now I have to go back and check, sorry, which one it is. And then it becomes negative here, okay? This one is more like leading and lagging relations. So the one on the left, the Granger one. So that's a little bit more complicated to discuss. I mean, but I take your point, and probably we have to look a little bit more into that. And probably I would like to enlarge the data set and use more stocks, because it could be more interesting. Having more sectors, you see, because here I just have 3 sectors which are all related to finance, so they're quite homogeneous, and I would like to see more heterogeneous stuff. So let me go to forecasting, and then I stop. So we do a rolling window exercise. Trying to forecast the 2012. Okay, so we do 1 step ahead forecast, and every time we compute the mean square error. Okay, and or we compute the maximum error across all units. Because given that we have resulted a uniform, so that therefore the max of all the errors across all units, it makes sense also to look at this, okay? Because this is an average measure, FE average. The other one is the maximum error that you can make. And then we report the median across all 252 forecast and the mean across all 2052 forecast. And this is the standard, and the SE is the standard deviation, okay? we have two ways to estimate the common component, which I didn't discuss. One is the restricted one, is based on this model where you can write the factor model as a standard way with just contemporaneous factors. And the other one is the unrestricted, where you cannot write it like that. And then we can use lasso, or you can use Danzig selector to estimate the VAR. So looking at these first 4 columns, you see that the restricted tends to be better than the unrestricted. Okay, these are assumptions that we cannot verify in practice, so you can choose to estimate the factor model in one way or the other. Okay, still, it's based on dynamic principal components, but used in different ways. Okay, the unrestricted one is a 3-step procedure actually, so that might be the reason that it goes a little bit worse. What becomes interesting is that if we compare to a univariate AR, then we tend to do better. Here you see, at least with the lasso. Here the Danzig selector with the unrestricted is not really working well, but with the lasso we do better. We do even much better if you look at the median, but that's already pointing to the fact that extreme errors might be an issue. And if we go at the max, you see the max using the median of all the max, which is the most robust measure. We obviously do much better. And then the last column is what is the Fan predictor. So the predictor used by Fan, Masini, and Medeiros in their very recent paper, where they do everything static in the theory. Then in practice, how do they forecast? They first filter with univariate AR1 filters the data. So basically the first column. And then on the residual, they do PCR, principal component regression. And then on the residual of that, they do a sparse VAR. Now, it seems, first of all, going from univariate AR to the whole farm predictor that I just described, there are not much gains, you see. I mean, look at 7.5, 7.6, 6.5, 6.2, 8.7, 8.7, 8.4, 8.2, okay, 8.3, okay. But what is important is that we beat them quite well, okay? Basically, this is it for the presentation, and then I'm happy to take questions and discuss other aspects if you wish. Here there are some references in case you're interested. Okay. I'm done. I'm finished.
Thank you very much. It was very interesting.
May I ask a question if no one wants to?
Okay.
So because I have difficulties grasping and interpretability of the model. Can you hear me well?
Yes, I can hear you.
Because so I understand that in some cases you want to filter out the common factor. For instance, if we analyze a European market, probably the common factor might be have interpretability as being a US market or so, because that affects one. But in some cases, I think that common factor might also originate from the internal network effect. So for instance, if I think of a partial networks, right? If I have a shock, depending on the structure of the network, it might be the case that if I have a shock in one node, it might, through the network effect, might have basically affect all the other stocks simultaneously, like in contemporaneous case, right? So in that sense, sometimes common factor might also take some part of the network effect, absorb some of that. And then the question, how do you, like, where is this a balance between them? And because, yeah, maybe you have mentioned that, but in that respect, how do you choose, for instance, the number of the common factors in the model and in the empirical application as well?
Yes. So starting from the last point, there are standard ways to find the number of factors. There's plenty of literature on that. I didn't mention any of it. In this particular setting where the factors are dynamic ones, what you do is you apply criteria looking at the eigenvalues of the spectral density matrix and averaging over all the frequencies. Or you could look at specific frequencies if you care about specific frequencies, okay? There are works by Onatsky, there are works by Mark Allen on this. In the static case, there are I don't know how many papers proposing different methods. So That's the reason why we don't do it, but clearly is an issue. Okay, I mean, I totally admit that in some settings it's clear that there is one factor, but already second one, yes or no, it can change things. And actually with Aaron, the same co-author of this paper, we also show that if you overestimate the number of factors, this might not be an innocuous thing to do. You might introduce a lot of misspecification there. And your first question, which I'm answering the second one, it's very good one, I think. In terms of interpretability, I agree that some network effect can result in factors. So what I could say is you could do both. You can first control for the factors and see what is the network, and then you do not control for the factors and see what is the network and compare the two. This could tell you something about it. I never thought about doing it, but I think it's a very, very nice question, and I like it. So I didn't try though, so cannot answer more than this, but thank you very much. That would be my answer. I mean, empirically, I would try to do something like that, and then building from there. So the issue is that factors are built on second moments, so covariances, while the kind of network that we look are built on the inverse of second moments. So the two things do not really speak with each other so much. That's where probably also the issue that you're mentioning can arise, but it's difficult to disentangle, okay?
Yeah, for sure. But in the simulation setting, you had one case where you had a non-identity contemporaneous matrix, right? But I think it might also depends like how dense that matrix is, and that might affect the identifiability.
So for the assumption of the model for the theory to carry through, that matrix cannot be too dense. That's a P times P matrix, but its eigenvalues must be bounded at any P. Otherwise, I violate the idea that that is idiosyncratic. So if that is dense, it means that there are common factors there. Yeah. And then probably they should have been carried in the first part. But I totally take your point. Thank you.
Yeah, thanks.
May I ask a question? How to extend your approach to integrated framework? So you should assume some form of integration in VAR part, right?
Right. Oh, that's a very good question as well. I don't know. I mean, I know from the factor part that if let me go back to one slide. Okay, it's better if we look at least one formula. So I've been working here, second block of equations. I've been working on this setting where X is in levels and they all have unit roots, and unit roots come from so the factors are co-integrated. So the second equation is actually a vector error correction model, should be written as a vector error correction model. And psi can also be I1. So there, one way to control for the factors is if you take that, one way to control for the common factors is estimate lambda through in first differences so that you don't have a spurious regression problem, and then project the data in levels onto the lambdas. Alternative by an angle, say estimate also the factors in first differences and then cumulate, okay? That's an alternative. So, and then once you control for the factors, you have the idiosyncratic component, and there I agree, I should do a VECM, which would be a large dimensional one. And I know there is some literature there, but I never worked on it. I guess I've seen a paper doing sparse VECM in high dimensions, but I'm not sure, but can complicate things quite a lot, I would say, but yeah, now this is a good challenge. Okay, I don't have an answer, but that's where I would start. For the common component, there are some results, so I would start from them. Okay, although admittedly they work for this restricted case, I don't know of results where they work for this unrestricted case where I have this VAR. because then here this a chi of L, as I said, is very complicated. So then that should address co-integration, and that would be much more complicated. But here, for the first part, lambda f, there is theory there. There is some theory. But although the theory is for simpler settings with not these nice inequalities that I showed you, but there is some theory there. For the xi, I assume there is, but I don't know exactly. So it's a good point, especially if one wants to go for macro, that could be interesting to see, or working with data in levels. I mean, instead of working with terms, work with prices. But yeah, thank you. Stimulating question. Yeah.
Any other questions? Okay, thank you again for very interesting talk, for discussion.
Thank you very much for having me.
Hope to see you in person in the future.
As well, yes.
Well.
As well.